All right, today is a beautiful, beautiful day in mathematics. I see the joy in people's faces as they look at what we're going to cover today, and I'm excited for you. So this will be a wonderful, wonderful experience. We've got a function we'll call f of x, and we've got another function I'll draw below it. We call it g of x, and we're going to bound it from a to b. And what we would like to do is we'd like to focus on that area between the two curves. Do we know how to find the area bounded between two curves? Yeah, it's no big deal. It's just f of x minus g of x, right? And that was easy. You guys have all finished those two assignments already. You're all caught up. So good for you. So as we look at this area, though, what's going to happen is we would draw a vertical rectangle in order to find that area. Does everybody agree? So, and the width of that rectangle is horizontal width. We would call it dx. But what if we wanted to take that area and we wanted to revolve it around the x-axis? The area right here between the blue and the red, and revolve it around the x-axis. We would get a three-dimensional figure that would be a solid, and it would be a cylinder, but it would be hollow, wouldn't it? Okay, it wouldn't be a solid all the way through. It would be hollow. Okay, right? Like maybe like if you're I don't know, maybe you're out hiking in the forest, you see a tree and it's rotted all the way through, right? You got like a bark on the outside, but the inside, little critters could run right through. Yeah. Okay. So that's what you get. And so what happens is if we revolve this rectangle around, what I'll try to do is I'll try to draw somewhat of a similar shape there. We're going to revolve this rectangle around to a symmetrical spot below. What we do get an interesting shape that's going on. We get a washer. One of the things I'm going to do for you over break is I'm going to try to put together a few videos where they actually show these solids being revolved around the x-axis. There is software that does that. I don't have the software personally. So I know it's challenging to look at it and see, okay, what does that three-dimensional figure look like? I can try to show you just a slice of it. You got this wash thing. Anybody ever cut up a pineapple? You ever core a pineapple? You take out the center, and then you cut up those slices. You get those pineapple slices. They kind of look like washers. Kind of same type of thing going on here, isn't it? So that's what we have. Now the cool thing is that when you get these washers, and you guys trust me, I know that they're not always easy to draw. I start with my washers like that, and I kind of make a little depth on the inside there. I make a little depth on the outside there. So and it's generally a pretty good shape. Part of the question is as we look at this is how do we come up with the volume of one of these? So as we slice this off, we're going to have, at this area of your rectangle, you're going to have an infinite number of rectangles. We're going to have an infinite number of washers as well. So, we see the center. The center is y is equal to 0. What forms this portion of the washer right there? G of x. So y equals g of x. And what forms the top part of the washer? Well, what's our formula for finding the volume of a washer? We know it has a thickness of dx, but how do we find, let's just start with the area of a washer. We got two shapes going on. They're actually the same shape, they're just different sizes. Circles. So if you want to find the area of a washer, what if you take pi times the large radius squared and then subtract the little one? Remember that? So we think about pi times large radius squared times pi times the little radius squared. We factor out the pi. Now in this problem, what's the big radius? What's the little radius? Very good. And so if I want to do an infinite number of them, I just slap on an integral, right? We have pi times the integral from a to b of big F of x quantity squared minus q of x quantity squared dx. So that's, really instead of using f of x and q of x, we should pick our middle part. Always f that's the big radius. That could change. This could be a general idea. Okay. So we want to do two examples today. Flip it over. And this is a complicated section, okay? Washers are not easy. And then after that, we need to do cylindrical shells, which are definitely very challenging. But then we're done with the unit, so we really want to make sure that we're not going to test like Wednesday get back. Next a couple days for yourself out, but we want to be caught up. That's a nice double sign examples. Great job. It was difficult. Thank you, P-Road. All right, so let's look. Then find the volume of the area bounded by y equals x squared and x equals y squared rotated around the x-axis. Ugh, what is this? What do the shapes even look like? And don't draw me. What do the shapes look like? Yep. So an upright parabola and a sideways parabola. So which part am I really focused on? That part right there, right? So I'm going to redraw it so I see really just that portion. Okay. Great. And what we're going to do is we're going to take that area, we're going to revolve it around the x-axis. So is it being revolved vertically or horizontally? It's being revolved vertically. So I'm going to draw a mirror image of it to the best of my ability. If I take that original area, would you draw vertical rectangles or horizontal rectangles? You could actually do either. Because I'm going to rotate it vertically, I am going to draw vertical rectangles so that I get a washer shape. A washer is something I can find the volume of. If I drew it horizontally, it would be tough for you to see right now, but you would actually get a cylindrical shell, and that we don't know how to work with yet. So, but if I draw this rectangle, and this is where people are like, well, how do you know? Well, you kind of got to visualize it, make a choice. So if I take that and then I rotate it around, do I end up with a shape that I know how to find the volume of? And the answer is yes. Okay. So the question is, how do I know which point to revolve it? So I chose this rectangle. See that? So that's the x value at which I'm choosing to work with. You could put the rectangle anywhere between these two spots. You'll still have you'll calculate the same volume of that washer, yes. Everybody convinced that I get a washer as a result of this. Now this three-dimensional shape that I get, is it hollow all the way through? Not at the very tip, is it? Okay. So like it might be like say a bowl that could hold water or something like that. Okay. Kind of an odd shaped thing, but whatever it is, let's find the volume of it. So here's the work that I like to put forth. I think that this is by far and away the best way to organize your work. I'd really encourage you to do so. We're going to make a washer right here. That's going to represent the washer on the inside. It's going to give me some room to kind of work. Somebody in last hour said that they were not able to draw washers, and my response was, if you're able to do AP Calculus, you can figure out how to draw washers. It might take some practice, but you can do it. I believe in you. They don't have to be perfect. So what makes the center of this washer? Let's identify that first. Y equals 0. Good. You guys notice how patient I'm being as I'm working through these. Take time. What makes this portion of the graph, the inside portion? Y equals x squared. What makes the top portion of the graph? X equals y squared. Yes. Okay, that's where we're stopping our rotation. Yeah, if you went past that, you would have to then switch what's on top and which is on bottom. That's a very good question. Okay, now the thickness is dx. Now we have something that's wrong here, though. What do you notice is different about how I have these things written? What stands out is what kind of looks like it doesn't fit. X equals y squared. So if I square root both sides, I get y is equal to the square root of x. And that is what we'll use then for that top one. Okay. So what we see here is that this distance is going to be big R from the top to the bottom. So the top is square root of x, and the bottom is 0, right? And that distance would be square root of x. This would represent my smaller radius, correct? Top would be x squared, bottom would be 0. That's a distance of x squared. So let's write the volume of one of these, just one. That's pi times big R squared, root of x squared, minus little r squared, x squared squared, then what? Times the width, which is dx. So again, that dx shows that everything matches through there. So we don't just leave that off. Great, that's the volume of one of the washers. How many would we like to do? How do we go from 1 to an infinite number? You see how we just say that like it's no big deal. Okay? I said, Kelvin, I have an infinite number of yard barber jobs for you this summer. You'd be happy to have the jobs, wouldn't you? When would you finish? You never would. Right, exactly. You would use the integral. So here, we just say no big deal. We're just like, hey, just put the integral on. So calculus is very easy to talk about infinite number of things. That's why calculus is so amazing. So now we have to consider the bounds. I'm looking at the original area. So this space right here, original area. So 0 is correct. Where do they intersect? Take a good guess. It's 1. So if you notice, 0, 0 is a point on both of those. And do you agree that 1, 1 is a point on both of those curves? Yeah, we could do the algebra and solve it, but we don't really need to. Antiderivative. Antiderivative x. Antiderivative x to the 4th. Evaluated. Go get some brain food, folks. Come back smarter, and we'll finish up these 2 problems. You guys are doing well. Good work. All right. So we we got this easy question now. How do we take the antiderivative? We already did that. We evaluated. Pi times 1/2 minus 1/5. Common denominator, 10, so 5/10 minus 2/10. So 3 pi over 10. There's the answer in all of its beauty. Yo. Okay, very good question. Do you see how you get 0? Okay, so if you have these two equations, x equals y squared and y equals x squared, then what I'm going to do is I'm going to take this y equals x squared, I'm going to plug it in for y. I'm going to substitute. I get x equal to x to the 4th. Good with that? Subtract the x, I get 0 is equal to x to the 4th minus x. I'm going to factor out, and I get x cubed minus 1. That's the difference of cubes. That factors, doesn't it? X minus 1, square the front, square the back, multiply 2 together, add. So you have solutions of 0, 1, and there are no solutions there. So 0 and 1 are 2 solutions. Easier to just guess. See what I'm saying? Generating reasonable guesses is a good mathematical strategy. So the point 1, 1 is on both those curves. So you can see that you go from 0 to 1. You could, but this is a horizontal parabola, so you'd have to use square root of x. And then yes, you could use the intersection on your calculator. All right, so let's try this one. This is our last problem. We have y equals 1 over x. What does that look like? Yep, has some asymptotes. We have x equals 2 and y equals 2. That will be in the first quadrant, so I'm not going to worry about the third quadrant portion of that graph. But I'm going to go to 1 and 2. 1 and 2. And I do like to label the graphs because I feel that it helps me as I organize my work. You guys do realize that, like, we spent like a number of days just practicing that, right? I mean, that's easy. This is challenging. It's hard to think back to when we were just taking antiderivatives and evaluating. I mean, that's really quite a simple skill now that we all just expect that we know what to do. But now, we've got the challenging part. So do you see the shaded region I'm going to be working with? Okay. Yep. It says that we're rotating about the y-axis. So I will get a mirror image over here. So do you think I'll draw vertical rectangles or horizontal rectangles? I will draw horizontal rectangles. What is the thickness of a horizontal rectangle? Thickness is dy. I rotate that around. I think I mentioned during second hour, and I probably didn't say it in a very kind manner, and I apologize. As a teacher, you often aren't able to take things back, but somebody asked about the complexity of the unit. I said, well, this is one you might have to rewatch the videos as you do the homework. And then they said, well, what if we don't have time to do that? I said, well, you probably just have to take a lower grade in class, I guess. And I don't think that they much cared for me saying that, but I don't know what else to say, folks. This is not easy material, and I can do my best to explain it all I want to, but there's going to come a time where you got to wrestle through it. So everybody see the shape that I'm generating here. Very good. Okay, so I kind of get a donut type shape. I've got a washer right here. Okay. I'm going to look at the middle of the washer. What generates the axis of rotation? X equals 0, thank you. I have a thickness of dy. I'm going to focus on the outside of the washer. What generates the outside of the washer? X equals 2. Again, so now you can see why I label my graphs. It's just a nice way of organizing your work. Okay, so now I've got this section right here. What generates that portion? Right, but all these are in terms of x, aren't they? So I need to solve for this in terms of x. How do I do that? Yeah, so I cross multiply, get 1 is equal to xy, and divide by y, and I get x is equal to 1 over y. So now they're all x equals. And that's a good thing. So I go through my work. So what is the larger radius? Very good. Larger radius is always 2. Now you recall that instead of doing top minus bottom, we do right minus left. So that 2 minus 0 is 2. And then the inside radius would be 1 over y minus 0, which is just 1 over y. So I'm going to write down the volume of one washer, pi times big R squared. What's big R squared? 4 minus little r squared dy. My favorite part, this is my favorite part. I know that seems weird, but my favorite part, hey, that's 1. How many would we like to add up? How do we do that? I mean, it's just just so amazing. It's incredible. It's like if you were asked to do an infinite of anything, what would you do? And it, like here in calculus, it's just take a 0. Yeah, there you go. You just take a 0. But here in calculus, it's no big deal. We're just like, well, integral, no big deal. It's incredible, the power of the integral. All right, so the bounds. Well, I look at my original area, and I'm looking at this region right here. So from your bottom to top. So what's this top portion? Y equals 2. Does anybody know what the bottom portion is? Jill? Jill, how do you get 1/2? You're looking at the intersection of those two, aren't you? So y equals 1 over 2, or 1/2. Very good. Notice how a reasonable graph can help us confirm that that's a reasonable choice, right? 1/2. It looks like it's lower than 1 and above 0, so there we are. So now it's this is a nice problem. Whoever thought of this problem is really, really good. Okay, so we've got pi times, what's the antiderivative for? 4y plus 1 over y. Very good. You guys are really smart. And 2 and 1/2. Oh, again, the 2. Y. I'm just going to attach the pi at the end. Oh, and I get 8 plus, what is 1 over 2? Oh, yeah, it's just 1/2, right? Then minus, sorry, I was jumping ahead. Then we plug in 1/2, we get 2. Plus, what's 1 over 1/2? That's 2. So it looks like you're going to have 8 minus 4, which is 4, plus 1/2. What's 4 plus 1/2? 4.5 or 9/2. So 9 pi over 2. And again, every time we do one of these type of problems, to me the answer just seems so special. We put a box around it. Yeah. Shiv, doesn't that looks pretty cool, doesn't it? That a boy. So put it Shiv, top left hand corner, top left hand corner. There you go. Yep, you're the man. All right, so you're ready for your next assignment.